So class 11, we're going to start by talking about relations. So graphing, interpreting, and modeling the relationships between two variables or two sets of data is an important goal for this course. So we're going to study all kinds of different relationships between two variables. In our earlier work with graphing, we've learned that two sets of data can be represented as an ordered pair, right? So whenever you have two pieces of data, you can let one thing be x and one thing be y, and then you can plot those things as x comma y. So for example, suppose we selected Jeff Green, Avery Bradley, Keith Bogans, and Gerald Wallace from the 2013 Celtics team roster, and we list their heights as 6'9", 6'2", 6'5", and 6'9", respectively. So you can write this correspondence between the name of the player and the player's height as an ordered pair. So you could put Jeff Green, comma, 6'9" inches, Avery Bradley, comma, 6'2" inches, etc. So the set of ordered pairs is called a relation. This completely describes the relationship between name and height. We call it a relation because it describes a relationship. And it's a relation is just any set of ordered pairs. Could be an infinite set, could be a finite set, like we have here with just 4 points in it. So the set of names, Jeff Green, Avery Bradley, Keith Bogans, and Gerald Wallace, that's the set of all first components, the x part of the ordered pair. That's called the domain of the relation. All the first things in the ordered pair is called the domain. And the set of heights, the second thing in the ordered pair, is called the range of the relation. So notice that in the range, I only listed 6'9" once. If something's in a set, you only have to write it down once. Okay, so here's just a picture of how we could explain the data. We're relating to every name, there's a height, right? So Avery, 6'2". Jeff, 6'9". Keith, 6'5", and Gerald, also 6'9". So in the ordered pairs above, we listed the name first. So the set of names is the domain, and the heights second. So the heights are the range. But we could flip them, right? We could just flip x and y, list height first and then name. So we would have 6'9" Jeff Green, 6'2" Avery Bradley, etc. Okay. So we're going to fill this in. Our domain now, the set of all first entries, is going to be the heights. So my domain is going to be 6 feet 9 inches. The stuff in the first entry, 6 feet 2 inches and 6 feet 5 inches. No need to repeat the 6'9". Only have to put it there once. And then the range is the names, right? So we've got Jeff, Avery, Keith, and Gerald. So I could draw arrows to represent what height goes to which player. So 6'9", that is Jeff Green and Gerald Wallace. So I've got an arrow from 6'9" to both of those players. And then 6'2", Avery, and 6'5", Keith. It's just a graphical way to represent the same thing we represent by listing ordered pairs. Now, though, suppose that we're going to give out an MVP award, a single MVP award, and we say, and the award goes to the player who is 6'9". Who gets the award? You don't know, right? Right. It's going to be a really awkward moment because two players are going to stand up, right? And then they have to go, oh, we meant the player who's 6'9" and whose name is Jeff, right? So this is an example of a relation that's not well defined, okay? Because you can't tell from something in the domain what belongs to it in the range. Okay, so this brings us to a big topic for the course, is functions. So our work in this course will focus on well-defined relations. So a relation, like we said, is just a set of ordered pairs, relationship between two variables. A well-defined relation, which is also called a function, has exactly one output for any input. Okay, so exactly one output for any input. You can't have two outputs for any input. So something that it would be a function, aside from this basketball thing. I always think of my television as a function. So I input some numbers into my remote, right? I type in 07, and what comes up? The news channels, NBC, I think. So type in 07, you get NBC. So we have one input, exactly one output. It would not be a good machine if I put in 07 and I wouldn't know what channel is going to come on, right? If there were two channels associated with one number, that would be a really bad machine, a non-well-defined relation. Okay, but on my TV, I have more than one channel that goes to NBC. So if you type in 7, you get NBC. If you type in, I don't know, 207 or something, you also get NBC. So it's okay if you have one element in your domain that, if you have two elements in your domain that go to the same thing in the range, two numbers that take you to the same TV station. That's okay. You're not going to call up the cable company and complain about that. You would call if sometimes you put in 7 and you get NBC and sometimes you get Lifetime. Right? You would call and complain that your TV is broken. So in the basketball example, come back to this for a second. Here's two relations. One, I list name and then height, and the other I list height and then name. Okay. They both represent a relation. So which set represents a relation? Both. Any set of ordered pairs is a relation, but only one of these is a function. And it has to be that each x can correspond to only one y. So which one is a function? P, yeah. The names correspond to exactly one height. Like Jeff Green is 6'9". He's not 6'9" and 7 feet, right? He's 6'9". One name, exactly one height to go with it. So P is a function. But H is not a function because there are two heights that correspond to, there's one height that corresponds to two different players, right? So if I say 6'9", you can't tell me who that is because there are two players. All right, so you try. We've got some relations here. Think about their domains and the range and whether or not it's a function. So you got to remember the definition of a function is that each input can go to one output. So think of it as like a computer database that you cannot confuse, right? So you put in the input, it should be able to go boom, pop up and give you the output. If there are two different outputs for that input, the computer just is thinking and thinking and thinking and you've confused it, right? So if I type Phoebe into this computer, what's going to pop out? 5, 5. If I type in Amy, what's going to pop out? Type in Katie, I get 3, 1. So none of these inputs confuse the computer, right? There is exactly one output. It can look it up and tell you. Okay, so is this a function? Yes, and its domain is the set of things that you type in, right? So we would have Phoebe, Amy, and Katie. And the range is the list of their heights. 3 feet, 1 inches, 5 feet, 5 inches. And again, you don't have to repeat the 5, 5 twice. It's in the set. You just write it once. All right, let's look at this next one with the ovals. If I type 0 into my computer database, what does it tell me? 7. If I type in 3, what do I get? -2, I get 7. 6, I get 7. I never confuse a computer, right? It always knows the answer. That makes it a function. My domain is all these things I typed in, 0, 3, -2, 6. And my range is just the single number 7. Okay, next one. I have just a list of points. So the x coordinate of my points, those are the inputs. I'm going to type them into my database. If I type in -1, what do I get? Good. If I type in 0, what does the database give me? 2. Type in 1, I get 5. Type in 2, I get 3. Type in 3, I get 2. So yes, this is a function. I never confuse the database by asking, if I give it an x, it always knows what y to tell me. So yes, it's a function. Its domain is -1, 0, 1, 2, 3, all the x coordinates. And then the y coordinates are 2, 3, and 5. And you don't have to write them in ascending order. That's just me. Any order is fine. Okay, last one. Let's hope this isn't a function so we can see one example that's not a function. I have a database. If I type a 3 into the database, what y coordinate is the computer going to give me? There are 2, right? So the computer can only do one thing. It has to pick one. So this is something that's going to confuse your computer, right? It's just going to get stuck in one of those loops to get the wheel spinning because it's searching and it's found 2 and it can only tell you 1, right? So this is not a function because 3 goes to 7 and 3 also goes to -4, right? So for the same input, for 3, you have 2 different outputs. That makes it not a function. But this is still a relation, and all relations have a domain and a range, so I can still write it out. -4, -3, 1, and 3. And the range is -4, 2, 4, 5, and 7. All right, does that make sense? A little bit? Okay, good. Okay, so we're going to look at graphs of relations and functions. So we've only analyzed them as points, looking at points, but you can always plot a point in the xy plane. So we're going to look at the graphs of these things. If our corresponding sets are real numbers, we can use a graph of the ordered pairs to determine if we have a relation or a function. The set of all x coordinates represents the domain, all y coordinates is the range, right? So we want to use the domain and range to determine if the following relation is a function. All right, so when x is -4, what's my y coordinate? 5. When x is -2, what's my y coordinate? When x is 0, what's y? When x is 1, what's y? I have 2. I have 2. This is a bad thing, right? For each x coordinate, there can be only one y, at most one y. So this thing right here, this point and this point together, mean that this is not a function. Right? And I can list the domain. Again, this is just the set of x values, -4, -2, 0, and 1. And my range is 5, 2, 0, and 4, and -2. So this is not a function because 1 goes to 2 different places, 4 and -2. And each input can't have more than one output. Is there a visual way that you can tell right away that this is not a function? Yeah, these 2 points, the thing that made this not a function, they lie on a vertical line. So this is something called the vertical line test. Many of you may have seen this before. If any vertical line intersects a graph in more than one point, the graph is not a function. So you imagine taking a vertical line, you start at the far left and you sweep it through the graph. If it ever hits more than one point, not a function. So this first guy is a function. It never hits in more than one point. But this guy, I'm sweeping it through, sweeping it through, sweeping it through, and bam, I hit a spot where that vertical line intersects more than one point. So not a function. Yeah, just depends on the y value. If there's more than one y value for any given x. Okay, so let's take a minute and just write down whether or not these things are functions using the vertical line test. So A, take a vertical line, start on the left, sweep it through. Does it ever hit in more than one point? Nope, so this is a function. Okay, B, lots of good discussion here. You start at the left, you sweep it through. It's fine, 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 fine. What happens right here? Still fine, right? Because if I draw, this is explaining the closed dot and the open dot is explaining what happens at 2. So if I draw a vertical line right at 2, it touches the graph at the closed dot, but not at the open dot. That open dot means that that's not included in the graph. So this is still okay. At 2, you're okay. And then after 2, still only touch once. So this is a function. Because that open dot means not included. Does that make sense? Okay. All right, how about this last one? Function or not a function? All sorts of wrong. We have lots of vertical lines that intersect in more than one point, right? All but one, yeah, just the 1 point. Yeah. So this is not a function. Great. Okay, so most of the functions that we're going to work with in this course are expressed as equations rather than as a list of ordered pairs. So in lecture 1, we worked with this equation, 4x squared plus 341x plus 3,194. You may or may not remember it. Y represented the average cost of tuition and fees for public U.S. colleges for the school year ending X years after the year 2000. The variable X is called the independent variable. You can assign any variable you want to X from the domain. And the domain in this situation is any non-negative number, right? So that would represent the number of years after 2000. The variable Y is called the dependent value because it depends on X, right? The cost of tuition depends on what year it is. And the value of Y is found after you select a variable for X. So our model defines a function because for each value X, there's exactly one value for Y. If I give you a year, you can tell me how much tuition cost in that year. And it's never two different numbers. It's not like, oh, well, in 2000, the tuition was $3,000 and $5,000. Can't have been both, right? So this is a function. So for any random equation, we want to determine whether or not it's a function. To determine it, you solve the equation for y in terms of x, and if there are 2 or more values for y for a given x, then it's not a function. So we'll look at a few examples. 3x minus 2y equals negative 12. We solve for y. So I'm going to subtract 3x from both sides. Then, Then I'm going to divide both sides by negative 2. So I end up with y equals 6 plus 3 halves x. Because you can divide that negative 2 into both pieces of the fraction. Negative 12 over negative 2 is 6. And negative 3 over negative 2 is positive 3 over 2. So for any x I plug in here, pick any random x you want. 5. If you put 5 in there, how many y's do you get? Just 1, right? 3 halves times, let's put in 6, it's easier. 3 halves times 6 is 9, plus 6 is 15. Any x, 1y. Any x in will give 1y, and that 1 is the important thing, right? So yes, this is a function. All right, how about x squared plus y squared equals 16? If I solve this for y, I'm going to have y squared equals 16 minus x squared. And then how do I get a y, plain old y, not a y squared? Square root, so I have y equals plus or minus the square root of 16 minus x squared. So let's pick an easy value for x. Let's say x is 0. If you put 0 in for x, what do you get for y? Plus or minus 4, right? So 0 goes to +4 and -4, right? For the input of 0, you get two outputs, 0, 4, and -4. So it only has to happen once, right? It only has to happen one time. One x value that gives two y values, and you're done. The whole thing's not a function. So I don't have to show that this happens all the time. I've got 1 point, I'm good. So this is not a function. It will happen consistently in this case, yes. You're going to get a positive and a negative. The only number you can plug in and you'll get one answer is what? 16. Yeah, 4. Yeah. If you put in x equals 4, when you square it, you get 16. The square root of 16 is 0, and plus or minus 0 is just 0. So there's one number you can plug in here, and you only get one output.
Is this actually the sideways function?
No, the graph of x squared plus y squared equals 16 is actually a circle with radius 4.
Okay.
So there are actually two values that if I plug in, I get only one y. 4 and -4. They give me y values of 0. Everything else will give me a +1 and a -1. A positive y and a negative y, not necessarily the number 1. So I plugged in x equals 0, and I got +4 and -4 as my outputs. So right there, I said, oh, fails the vertical line test. Okay, here's a big thing. We're going to use this notation for the rest of the semester. It's pretty important. Function notation. Here's a table. It lists the height of a baseball given in feet at various times x in seconds. So we've got time on the bottom here. We've got the height of the ball above there. The values listed represents or defines a function. Y is a function of x. Instead of using the variable y, okay, like you have for much of your mathematical life, instead, we're going to use letters like F, G, and H, or capital F, G, and H to represent functions. So instead of y, we're going to use these things. F is the most common one because the word function starts with F, right? And then because we're very creative, after we use F, we use G and then H. So we can represent the function using a notation where we say y is equal to f at some x value. Okay, so the expression f of x does not mean that f and x are multiplied. It's a really common misreading if you haven't had this presented to you before. You would read it as f of x, and it means the value of the function at a certain x value. So the input is denoted by x, and the output is f of x. So f of some input gives you an output. So y and f of x are synonymous, right? So where you used to say y, now we're going to say f of x. So for this particular function with the baseball, our input is time in seconds, and we're going to look at how to evaluate and interpret function notation. So that thing in parentheses is always an x value. It represents an input or an x value. And when I write f of 2 equals, I'm saying, okay, 2 is the input. What's the output that corresponds to 2? 99. Okay, so this is 2 seconds. It's asking me to find the output, which is the height of the baseball, when the input is 2 seconds. And I get 99. And I should be able to write a sentence, f of 2 equals 99, that explains what that means. So I would say the height of the ball after 2 seconds is 99 feet. Okay, how about f of 0? What does f of 0 equal? 3. So this just says, tell me what the y is when x is 0. That's all f of 0 means. And this is asking us to find the output when the height is 0 seconds. So when I interpret this, this says at 0 seconds, the height of the ball is 3 feet.
So these answers are still y.
These are y's.
Just f of x is y in terms of x.
Yeah, yeah. So instead of writing x comma y, right, we now can write x comma f of x. And it's the same thing. This represents 0 is the x and 3 is the y. So we could write 0 comma f of 0 or 0 comma 3. These are just sort of all the same thing. So the f of x notation, it just carries a little bit more information. Instead of writing y equals 3, f of 0 says y equals 3 when x is 0. Right? So it carries the x coordinate that we're talking about in its notation. Yes.
How do we know that we're asking for the height rather than the other way around?
Where I was- because it's always y in terms of x.
Yeah. So the x, or the input, is always the thing in parentheses, and the thing outside that it equals is the output, or the y. And I think I said when I described this guy, the height of the baseball is y,
That's where
and the time is x. Because of that sentence, yeah. So this is what explained which one was the x and which one was the y, which one's the input, which one's the output. Yeah, oh yeah, that should definitely always be clear.
Which should be clear because height is dependent.
Yeah, and particularly in a physical example, like in a real world thing like this, the height depends on how much time has passed. Definitely, yeah. Okay, so what if I asked you, when does f of x equals 103? I'm asking for the input, and I'm giving you the output was 103. 103, yeah, when x equals 2.5. So now they're giving you the y and asking for the x, and you would say, oh, when x equals 2.5. And that says the height is 103 feet after 2.5 seconds.
I'm sorry.
That's okay.
For C, you just put f and then 2.5 equals 103.
Yes, right? Or you could write f of 2.5 equals 103. Yeah. Yes.
Okay, this might be a little bit of a so to make this like graph here to like scale, would you use like for example, you have to have the speed of the ball to like make it like, you know, it goes so fast, but how would you end up incorporating that? Just curious.
How do we use the speed of the ball to help us draw this graph?
Yeah, to like
Okay.
scale. Like, how do we-
So there are standard equations from physics that allow us to predict the height of some object that we throw, because we know how gravity acts, and we know that we can counteract some of gravity by how fast you throw the ball up in the air. So we don't have all the mathematics to explain why the equations are what they are right now. Keep going, you'll see it in Calc 1. But in general, the height of any falling body at a given time t, I want to see, what are we working in here? Feet? Yeah, it's negative 16 t squared plus v naught t plus h naught. And, you know, it looks crazy. V naught, that means initial velocity or speed, yeah. And the little sub-zero, You read that as not, as in N-A-U-G-H-T, not, nothing, right? It represents velocity at time 0. That's why we put a little 0 there. Initial velocity or velocity at time 0. And H naught represents initial height, or the height at time 0. So like if I'm throwing something up in the air, its height at the moment I release it, that would be the height at time 0, would be like about 5 feet. And whatever speed I use, I would just plug in here, and then I could predict the height of the ball at any given time. Okay. So here I have it written here, right? I can represent this function that models the height of the ball with an equation, f of x equals negative 16x squared plus 80x plus 3. So the negative 16, that has to do with the acceleration due to gravity. The 80 is my initial speed of the ball. So that means I threw this ball up at 80 feet per second when it left my hand, and it left my hand at 3 feet, right? So I let go right here. So if I wanted to use the equation to represent f of 2, that means making the x2 in the parentheses of the f, right? F of 2. That means put 2 in for all the x's in the equation. So this is just asking what is y when x is 2. So I plug in 2 for my x's, negative 16 times 2 squared plus 80 times 2 plus 3. So that's 4, that's negative 64 plus 160, it's 96 plus 3 is 97. I don't think that's right. 99, yeah. But I did it right though? Other than that? Okay. So 99. So 99, and yeah, if I go back and look at my table, f of 3 is 99. Oh yeah, I was plugging in a 2. F of 2 is 99. Sorry. F of 2 is 99. Does that make sense that it's at a height of 99 seconds at 2 and at 3 seconds? How does that make sense? Because it's coming back down, yeah. So at 2 seconds, it hits 99 feet. It goes up a little further and then starts to come back down, and it's going to be at 99 feet again. Okay, so if I wanted to use the equation to solve f of x equals 99, that means I would replace f of x with a 99, right? Those two things are equal. I can just substitute one thing for the other in the equation. So instead of writing f of x equals that whole thing, I write 99 equals that whole thing. And how do I solve this? Algebra, yes. Can we be more specific? Subtract 99, we gotta have 0 on one side. Minus 96. And then quadratic formula, I could try to factor. I think it does factor, but I'm not going to bother. Let's use a quadratic formula. So x equals negative 80 plus or minus the square root of 80 squared, which is 6,400, minus 4 times negative 16 times negative 96, all over 2 times negative 16. So let's have my calculator do the work here. Negative 80 plus, I'll do the plus first, the square root of 6,400 minus 4 times negative 16 times negative 96. And then I'm going to divide all that by negative 32. 2 times 16. And I get 2. So x equals 2 is one of my answers. And then I have to do all of that work again, but this time I'm going to do negative 80 minus the square root, because this is plus or minus, so you got to do 2 calculations. So this time I go up here and I do minus, and I get 3. right? So I get 2 and 3 seconds as the times where my height is 99. Is that accurate? Yep, going up to the table. Yep. The height is 99 at 2 seconds and at 3 seconds. So here's a graph of this function. Yes?
Something like quadratic. Did you factor out a 16 or?
I believe 16 does go into all 3 of these numbers. So yeah, once you factor out a 16, it's probably a lot easier to factor.
And
Yes.
you by zeros.
Yes, and then you divide both sides by 16. You mixed it up with 0 can be divided by anything,
Yeah.
but nothing can be divided by 0.
Yeah.
Right. So the graph of the function, this is a graphical representation of a function, can be found just by plotting the various ordered pairs x comma y in the coordinate plane. So I have the points plotted here that correspond to the numbers that were in the table, but I could plot, there's actually an infinite number of points to plot, right? I could plug in, instead of just 0 and 0.5, I could put something in between there and get another point, right? So I have this infinite number of points that represents the height of the ball at any moment in time. So if I want to use the graph to evaluate f of 4, how do you think I would do that? Look at where 4 is on the x-axis or the y-axis? X. Because this x-axis is time, the y-axis is height. So I'm putting a 4 into f. That means it's an input, it's a time. So I go to 4, I go up to the graph, and I see that the y-coordinate at that point is 67. So f of 4 is 67. And you can see that if that point weren't labeled, you could figure it out by going over and looking at the y-axis. How about if I wanted to solve the equation f of x equals 67? What x values make 67 give a height of 67? 1 and 4. So I've got this horizontal line here at 67, and I say, oh look, there are 2 x values where the height of the ball is 67, 2 times, 1 second and 4 seconds. Okay, so now you have a little bit of work to do to practice with function notation.